Okie dokie. So, concave mirror, a spherical concave mirror. I know it doesn't look like a sphere, but spherical concave, this is like you're looking in a mirror, like the inside of the spoon, okay? And in this case, we've got, here's the mirror. This is the principal axis. The principal axis we use for reference purposes for measuring things. The problem's given the mirror, which again is part of a sphere, so it has a center radius of 3 meters. I should have put an R. Our radius is 3 meters, and the radius goes from the center of the sphere out to the mirror. That's 3 meters. And remember that the focal length, which goes from the mirror out to the focal point, is half of the radius, and so that's going to be at 1.5 meters. And I've already measured these out for you. I drew these to scale. You don't have to draw them to scale, but I've done that. And then the object is 5 meters away from the mirror. That's D subscript O, and I've shown that I've decided to make it 7 centimeters tall. That's the size of the object, and we're looking for the image size, the image location, the magnification, and the image size. Okay, so when you're doing these things, I'm going to draw the ray diagram first. The first ray that we always draw is parallel to the principal axis from the top of the object. Here's the object represented by an arrow from the principal axis up. And that black arrow represents the 7 centimeters. All right, that black arrow pointed up because I'm saying the object's upwards, not upside down, but upwards. And that's the object. Okay, so you draw in a light ray traveling from the principal axis to the mirror. And you know the definition of the focal point. We covered this in class. The definition of the focal point is when in any parallel light ray, any light ray that's parallel to the principal axis will reflect through this point called the focal point. Okay, so this is a light ray, so don't forget the arrow. Comes in parallel to the principal axis, strikes the mirror, and we know, this is the reason why we use this ray, we know it reflects through the focal point. That's how that light would reflect, obeying the law of reflection. Now, you only need 2 light rays to figure this out. So there's one, follows that path. We actually have 3 we can choose from. Actually, there's even 4, but there's 3 that are fairly easy. The second one that I frequently use is going from the top of the object through the focal point to the mirror, and then it will reflect back parallel. See, all of these things are reversible, and so if a light ray that travels parallel to the principal axis reflects to the focal point, then a light ray that travels from the top of the object through the focal point would reflect back parallel to the principal axis. Okay, so don't forget that's an arrow. It's going to reflect back parallel to the principal axis. Okay, so there is the second ray, and now the object, or the image, is where this is called the image point. That's where your focused image would be. Okay, your focused image would be right there. It would be that tall. Notice the arrow is upside down, so it's inverted. It's flipped upside down. This would be a real image. It's real because the light rays really did come to a focused point. All right, these are real light rays that have been reflected to that point. There is a third ray that you can check, you can draw to just check your answer, and that ray would go from the top of the object through the center, which is right here, the center of the sphere, and it should meet at the same point, and it does. That ray is one that goes to the mirror and it reflects right back on itself. Okay? So, this upside down arrow represents HI. That's the height of that thing, and the location of that from the mirror is DI. It's positive because remember, these are light rays reflected back. It's positive because they really do meet at this point, so it's a real positive value for that DI. And that would be a negative value for HI. And I could measure these things with the ruler if I chose to, because I did draw this to scale, where every 10 centimeters represents a meter for the distances. So that's why that's 50 centimeters away, representing that 5 meters. So this comes out to be, looks like 20 centimeters, which would represent 2 meters. So according to my drawing, the value for DI is 2 meters. And the value for HI is going to be negative because it's upside down. And so here's, oh, you know what? I forgot to draw that to scale. Whoopsies. Bad teacher. I forgot to draw that to scale, so I'm not going to be able to do that. I'm going to calculate it mathematically anyhow. But yeah, I know it's going to be negative and it's going to be smaller than that, right? Notice how small that arrow is. Notice how big that one is. So the image has been reduced. Let's go ahead and calculate this mathematically. So to find this value of DI mathematically, use your mirror equation. 1 over F equals 1 over DO plus 1 over DI. And so solve for 1 over DI. That's going to be 1 over F, so you have to subtract 1 over DO to the other side. So that's going to be 1 over F, which is 1 over 1.5, minus 1 over DO, which is so that's minus 1 over 5. And I've already calculated this out. So this comes out to be 0.467. So you have to take the reciprocal of that, right? Because that's 1 over DI. I want to know the value of DI itself. And that came out to be 2.14 meters. And it's positive, and so it's real. That's a real image because it's positive. Notice I was pretty close in my drawing. The actual mathematical answer is 2.14. I had estimated here, too. To find the magnification, remember the magnification equation is negative DI all over DO. So that's negative. That's part of the equation, right? Negative 2.14. DI is positive, but there's a minus sign in the equation. So minus 2.14. That's the image distance over the object distance of 5. And so this comes out to be, let me see, that's negative 0.43. You put an X for times, the magnification. It's less than 1. The absolute value of this is less than 1, which represents the fact that it's smaller. Okay. And again, the X is just times. When you talk about something that's magnified so many times. Then, to find the image height, magnification, there are 2 equations for magnification, right? It's negative DI over DO, but it's also the ratio of the size of the image to the size of the object. That's something you knew before you ever came into my classroom. When something's magnified so many times, saying that the image is either bigger or smaller than the object by that many times. So we know that negative 0.43, that's the magnification, equals HI, which is what I'm looking for, divided by that object height of 7 centimeters. So divided by 7. So I'm going to multiply 7 to the other side, and I'll get that HI equals 7 times negative 0.43, which is negative, where is it? Negative 3 centimeters. So that's the size of the image for that candle, that candle flame lab. If you've done that lab, where we have a candle flame as the object, and we look for the image of the focused image of the candle flame, which we always found to be upside down. That's what this would represent, would be that image on the piece of paper of the candle flame. Okay, it's upside down. Notice the arrow's upside down. Negative sign here, negative sign here. So it's inverted. Again, the negative sign represents the fact that it's inverted for the magnification. What do I mean by inverted? I just mean it turns upside down. Okay. And that's also representing that it turns upside down. So, concave mirror. Next example will be another one with the same mirror, but in a different location. The object will be in a different location.